finally made it. Let's all finally made it. I finally made it. I fucking made it. 7 Montreal painters. Guys, I have such a headache, and you know nothing fixes it better than machine learning. Andrew Ng, let's watch him again together, all of us. Can't wait to open Kaggle and do XG boost on the dataset from Spotify. Dude, we are session 14.
Welcome to 6229 Machine Learning. Some of you know that this concept.
Expectation, maximization, algorithmization.
Let's get started. So, let's see, logistical reminder. The class midterm is this Wednesday, and there's 48-hour take-home midterm. And the logistical details you can find at this Piazza post. Right? So midterm will start Wednesday evening. You have 48 hours to do it, and it's submitted online through Grayscope. And because of the midterm, there won't be a section this Friday. Oh, and the midterm will cover everything up to and including EM, which we'll spend most of today talking about. Okay? Certainly, don't look so stressed. It'll be fun. Well, maybe. All right. So what I'd like to do today is start our foray into unsupervised learning. So far, I've spent a lot of time on supervised learning algorithms, including advice on how to apply supervised learning algorithms. In which you'd have, positive examples and negative examples, and you run logistic regression or something, or an SVM or something to find the line, find the decision boundary between them. In unsupervised learning, you're given unlabeled data. So rather than given data with X and Y, you're given only X. And so your training set now looks like X1, X2, up through XM. And you're asked to find something interesting about the data. So the first unsupervised learning algorithm we'll talk about is clustering, in which given a data set like this, hopefully we can have an algorithm that can figure out that this data set has 2 separate clusters. And so one of the most common uses of clustering is market segmentation. If you have a website, selling things online, you have a huge database of many different users and run clustering to decide what are the different market segments, right? So there may be, people of a certain age range, of a certain gender, people of a different age range, different level of education, people that live in the East Coast versus West Coast versus elsewhere in the country. But by clustering, you can group people into different groups, right? So I want to show you an animation of really the most commonly used clustering algorithm called k-means clustering. And let me show you an animation of what k-means does. And then
show us the animation.
And talk about how you can implement it. So let's say you're given a data set like this. So all these are unlabeled examples. So just X plotted here. And we want an algorithm to try to find maybe the 2 clusters. The first step of k-means is to pick 2 points denoted by the two crosses called cluster centroids. And the cluster centroids are your best guess for where are the centers of the 2 clusters you're trying to find. And then k-means is an iterative algorithm, and repeatedly you do 2 things. The first thing is go through each of your training examples. Oh, I'm sorry. Almost. Okay, thank you. All right. Okay. Let me know if it happens again. Okay. Right. So you guys know that, right? So right, 2 cluster centroids. So the first thing you do is go through each of your training examples, the green dots, and for each of them, you color them either red or blue, depending on which is the closer cluster centroid. So here we've taken every dot and colored it red or blue, depending on which side it is, which cluster centroid is closer to. And then the second thing you do is look at all the blue dots and compute the average, right? Just find the mean of all the blue dots and move the blue cluster centroid there. And similarly, look at all the red dots, and look at only the red dots, and find the mean, find the, oh, what's wrong with this? That's it, oh, it's very strange. All right, apparently if I keep moving my mouse, it doesn't do that. All right, thank you. And then find the mean of all the red dots and move your red cluster centroid there. So let me do that, right? So the cluster centroids move as follows to the mean of the red and the blue dots. And this is just a standard arithmetic average. And then you repeat again where you look at each of the dots and color it either red or blue, depending on which cluster centroid is closer. So I'm going to recolor every point based on what's closer. So that's the new set of colors. And then the second part of the algorithm was again, look at blue dots, find the mean, look at red dots, find the mean.
Come on.
And then move the cluster centroids over, excuse me, to that mean. Okay? And so, and it turns out if you keep running the algorithm, nothing changes. So the algorithm has converged. So if you look at this picture and you repeatedly color each point red or blue, depending on which cluster centroid is closer, nothing changes. And you repeatedly look at each of the two clusters of colored dots and compute the mean and move the clusters there, nothing changes. So this algorithm is converged even if you keep on running these two steps. Okay? So let's see. Let's write down in math what we just did. All right. So this is a clustering algorithm, and specifically, this is a
K-means. I heard K-means a lot. Clustering. So what is K-means? We have K-center. Like we have a bunch of data, and we wanna. I think that's it. I heard the term before. I didn't study it well. So the idea is that we have a data set and we want to classify it or clusterify it into K clusters. And we need to find K points which stand for the center of those clusters. How do we do that? So that once we make a circle around each of those means, each data set belongs to the closest center or mean. I think that's K-means cluster, which is very interesting.
So your data set now does not come with any labels. And so in K-means, step one is initialize the cluster centroids. Right, I'm going to call them mu1 up to mu k randomly. Right? So this was a step where you plot down the red cross and the blue cross. And when I did it on the PowerPoint, I did it as if we would just choose these as random vectors. In practice, a good way actually the most common way to select the random initial cluster centroids isn't quite what I showed, is to actually pick K examples out of your training set and just set the cluster centroids to be equal to K randomly chosen examples. Right? So in a low dimensional space, like a 2D plot, they could do on the diagram, it doesn't really make this random vector. It's clustering algorithm. So your data set now does not come with any labels. And so in K-means, step one is initialize the cluster centroids. Right, I'm going to call them mu1
Okay,
up to
how
mu
do
k,
we find these K centroids? Just random?
So this was a step where you plot down the red cross and the blue cross. And when I did it on the PowerPoint, I did it as if we would just choose these as random vectors. In practice, a good way actually the most common way to select the random initial cluster centroids isn't quite what I showed, is to actually pick K examples out of your training set and just set the cluster centroids to be equal to k randomly chosen examples, right? So in a low-dimensional space, like a 2D plot, like a two diagram, it doesn't really matter. But then when you work with very high-dimensional data sets, the more common way to initialize these is just pick, k training examples and set the cluster centroids to be at exactly the location of those examples. But in low-dimensional spaces.
So what will we do if it was me? So we have k initial sample, and then we want to update this k to find a better k set of centroids. What do we have in mind? Let's give ourselves some time to think about it. Yes, it is pretty. Whose birthday is it? Oh, I know whose birthday it is. Yeah. So, projects, thesis, ChatGPT, ML. Okay, that's a good one. How did I share everything? What happened? Make sure both devices use Bluetooth. Well, the Bluetooth is on. Oh. Why are you disconnected? Update. Verify identity. Do that. Okay. Perfecto. Sounds good. And now I have this page, right? Smart view. Okay. Perfect. Start now, yeah. Perfect. Okay. Perfect. So what is this story? We have a data set, right? Are they labeled or not? I don't know. So we have stars, couple of them, and then we have another color. So we wanna have like K. Probably one of them is here. And what we want is that find 3 centroids. And okay, so it says take 3 from the beginning base or any point. mu1, mu1 1, right? mu2 1, mu3 1. All right. Are these good enough? for the centers, because we want to have these circles around. Let's assume that we know the labels, right? What if I knew the labels? I would get the mean of the, right? This training data set here, I would get the mean of the each coordinate, and then I would update this mu1 2, then it would be like mu1 3 and mu3 2, mu2 2, right? Updated. Well, that would be end of it. So probably it is not labeled already, right? Our data is not labeled. Okay, if the data is not labeled, what would we do? Let's assume we have these red dots all over. And we want to have 3 points as the centroids. Right? Well, what would I do was first choose 3 points, or any 3 points, right? They are not labeled, so I would connect these lines, right? Choose the middle of them and draw a circle with the minimum, or a sphere. What should be our updating route? That's the question. And that's what Andrew wants to tell us. I don't have time, dude. Let's go watch it.
It does make a big difference. And then next, you repeat until convergence.
Repeat until convergence.
Step 1 is so this is a
arc mean.
Just write this down.
Color the points. So we have j point, n points. Where are the xi coming? Oh, okay, minimum distance from mu j. Perfect, is called cj. And then mu j, you update mu j by the weight. The weight is ci equals j.
So that makes sense. So the 2 steps you would alternate between. The first one is set ci for every value of I. So for every example, set ci equal to either 1 or 2, depending on whether that example xi is closer to cluster central 1 or cluster central 2.
What does ci equal j mean?
So just take each point and color
ci
the
is
red.
a number.
And represent that by setting ci equals 1 or 2, if you have 2 clusters, if k is equal to 2.
Let's go see what it means here, right? says mu j a set ci. Well, the set is xi. We have the set of xi's, right? So I is the counter for the whole number of data. And we have, for example, 3 clusters. So ci is argmin j xi minus mu j norm 2, and then b for each j, m is the number of cluster, which is 3. We say mu j, the updated version is, I want to m, well, I should not be, okay, we have k clusters, m is the number of data sets. Well, I want to say, yeah, okay, k and m. So I is 1 to m, j is 1 to k. I 1 to m, 1 ci equals j xi over 1 to m right. Let's see what it means here. So we have 3 points, right? We have this one, this one, this one as our mu1, mu2, mu3. Then it says for each data set, right? C1, Ci for each xi, this is our xi, right? Ci is the argmin j xi minus mu j. So Ci is the closest centroid to our data set. So for example, xi for this one, for this data set is mu3 because it is closest. So, okay, which makes sense, right? To each data point, right? We say each data point is close. What centroid is closest to our centroid? So all of these, for example, belong to all of these belong to this mu3, probably, right? Then there are some that belong to mu1, right? These all belong to mu1. All of the dots inside this. Also this, and they all belong to mu3, and they all belong to mu2, right? Perfect. They all belong to mu2, and then you update mu1 hat. Mu1 will be mean of, okay, that's very beautiful, right? Which makes sense. So we have an initial point, set of points. Then we say which set of centroids, initial centroids, we take data points that are closest to those centroids compared to other centroids. This is our initial clusters, right? We have it in the light blue, sky blue, then we have it in green, then we have it in black. It's pretty much mutually exclusive partition of the data set, unless like some data points, for example, if there is a data point that is exactly equal distance from two centroids. In that case, probably we assign it to the lower index centroid, for example. Then what we are doing to do is how we wanna mu1 hat, mu1, update mu1, mu2, mu3. So now it says mu1, and the new mu1, which I wanna write it with another color, purple. New mu1 is all of the ones that are in this, for example, light blue cluster will be the mean of them. So I will draw the mean of them, and it probably is somewhere here. So this is the mu1 hat. Mu1 hat, then there will be mu2, mu1 new, mu2, then this will be mu3, right? And then we again find which data points are closest. Probably this time it won't change much. Like mu3 may include a new point from the previous data set, may not. And then after a while it converges. I can see that. I can see actually that this converges pretty fast. My intuition says. Perfect. That was a nice idea.
Oh. The notes say L1 norm squared from this morning.
Brilliant. Simple.
What notes was sent out this morning? Oh, that's weird. It shouldn't be L1 norm. If it says L1 norm, that's a mistake. Sorry about that. But usually, and it turns out whether you use L2 norm and L2 norm squared, they give you the same answer because the argument is the same either way. But it's usually, do we have a typo in the notes? Oh, I see. Oh, got it. Okay. Looks like in the notes we wrote that. Okay, cool. But by default, when we write that norm, we actually we mean L2 norm. Yeah, right. By default, this is the L2 norm of X if it's unspecified. If it's L1 norm, we usually write this. So L2 norm is more common, and with or without the square, you get the same result. Okay, cool. Thank you. All right. So let's color the dots. Paint each dot either red or blue. And then for this, this is, sum through your examples and take all the examples, assign to a certain cluster, right? Assign to cluster J, and set mu J to be average of all the points assigned to that cluster J. Yeah. Oh, sure.
Okay, so we got how it works. Wasn't it better, however? We know Andrew. Well, was Andrew the best instructor? No, this guy was the best instructor. We used to ask questions and follow up with the students if they... Alright, wasn't it better if Andrew explained it first on the point date, like with the shape, and then algebraically formalize it, or no? I think that was better. I would have done. What is the difference? We don't care about better or not. Fuck that. Let's just learn and go ahead.
All right, none of the black markers are working.
Optimization is the route to mental masturbation.
Is there part of this is unclear? If this part is you can't see, I'll write it out. Oh, sure. Hi, do we have lights in front? Okay. Got it. Let there be light. All right, awesome, great. That was an easier request to satisfy. That was. Okay, oh, I just want to let you look at it for another minute. All right, is it okay? Thank you. Oh, great, this wasn't on. Okay, all right, now I can move it up. All right, So it turns out that this algorithm can be proven to converge. Exactly why is written out in the lecture notes. But it turns out if you write this as a cost function, right? So the cost function for a certain set of assignments.
So the sum of the distances from the... So this minimizes this cost function. I take it, yeah.
Points of examples to cluster centroids, and for a certain set of positions to the cluster centroids. So C, these are the assignments. And these are the centroids. Right? So this cost here is sum over your training set of what's the square distance between each point and the cluster centroid that is assigned to. So it turns out, I won't prove this, a little bit more details lecture notes, but I don't want to prove this. It turns out that on every iteration, k-means will drive this cost function down. And so, beyond a certain point, this cost function can't go any lower, or this can't go below 0, right? And so this shows that k-means must converge, or at least this function must converge, because it's a strictly non-negative function that's going down on every iteration, so at some point it has to stop going down. K-means that converge. In practice, if you run k-means in a very, very large data set, then as you plot the number of iterations, J may go down, and just because of
so
lack of
very
compute or
fast.
lack of patience, you might just stop this running after a while. It's going down too slowly. So that's k-means in practice, where maybe it hasn't totally converged, we just cut it off and call it good enough. Now, the most frequently asked question I get for k-means is how do you choose k? It turns out that when I use k-means, I still usually choose k by hand, and so and this is why.
By hand,
which is,
dude, that's it. Machine learning is an art.
Unsupervised learning, sometimes it's just ambiguous, right? How many clusters there are. Right. With this data set, some of you will see 2 clusters, and some of you will see 4 clusters. And it's just inherently ambiguous. What is the right number of clusters?
Ooh, what if the dimensions are high?
You can find online the criteria like AIC and BIC for automatically choosing number of clusters. In practice, I tend not to use them because I usually look at the downstream application of what do you actually want to use k-means for in order to make a decision on the number of clusters. So for example, if you're doing a market segmentation, because your marketers want to design different marketing campaigns, right, for different groups of users, then your marketers might have the bandwidth to design 4 separate marketing campaigns, but not 100 marketing campaigns. So that would be a good reason to choose 4 clusters rather than 100.
That's very related to our research.
Clusters. So it's often, if you look at the purpose of what you're doing this for. I think in the programming exercise, in the homework, you see a image compression exercise where you want to cluster colors into a smaller number of clusters. You implement this. It's actually one of the most fun exercises, I think. But so there you be saying, well, how much do you want to compress the image to decide how many clusters to try to use? Okay, so I usually pick the number of clusters, either manually or looking at what you want to use k-means cluster for. If you're trying to cluster news articles, like the Google News example, I think I showed in the first lecture, you say, well, how many clusters kind of make sense for news articles? Okay, all right, that's a question. So, yeah, good. Oh, sure. Well, k-means get stuck on local minima. Yes, k-means just stuck to local minima sometimes. And so if you're worried about local minima, the thing you can do is run k-means, say, 10 times or 100 times or 1,000 times from different random initializations of the cluster.
Oh, so it doesn't have a... We may not end up in a global minimum? That doesn't make sense.
And then run it, say 100 times.
Because it should converge to a global, I guess.
And then pick whichever run resulted in the lowest value for this cost function. Okay.
Mm-hmm.
The k-means algorithm typically involves two main steps that are repeated until convergence. Assignment step, assign each data point to the nearest cluster center. Update step, calculate the new cluster centers as the mean of the data points assigned to each cluster. The algorithm iterates over these steps until the cluster assignments no longer change, or a specified number of iterations is reached. Here's a breakdown of the steps in a bit more detail. Initialization, choose the number of clusters k and initialize the cluster centers. This can be done randomly or by using methods like k-means++. Assignment. For each data point, calculate the distance to each cluster center. Assign the data point to the nearest cluster center. Update. Calculate the new cluster centers as the mean of the data points assigned to each cluster. Repeat. Repeat the assignment and update steps until the cluster assignments do not change. Convergence.
In the programming exercise. Now, there's a problem that seems closely related. But it's actually quite different when you derive the algorithms, which is density estimation. So let me motivate this. I actually have some time back, had some friends working on a problem, which I'll simplify a little bit, if you have aircraft engines coming off the assembly line, right? And every time an aircraft engine comes off the assembly line, you measure some features of this engine. So you measure some features about the vibration, and you measure some features about the heat that the aircraft engine is producing. And let's say that you get a data set, right, that looks like this. Okay. And the anomaly detection problem is if you get a new aircraft engine that comes off the assembly line, and if the vibration feature takes on this value and the heat feature takes on this value, is that aircraft engine an anomalous one. This is an unusual one, right? And so the application of this is that as your aircraft engine comes off the assembly line, if you see a very unusual signature in terms of the vibrations and heat the aircraft engine is generating, then probably something's wrong with this aircraft engine. You have your people, have your team inspect it further or test it further, before you ship the airplane, before you ship the engine to an airplane maker, and something goes wrong in the air. There's a major accident, a major disaster, right? And so anomaly detection is most commonly done. Well, one of the common ways to implement anomaly detection is the model P of X, which is given all of these blue examples, given all of these dots, can you model what is the density from which X was drawn? So then, if P of X is very small, then you flag an anomaly, right? Meaning that, gee, I think something's funny here, and maybe someone should inspect this aircraft engine a little bit further. So anomaly detection is used for tasks like this, for inspection tasks like this. Is used for, many years ago, I was actually working with some telecoms providers, helping out telecoms company on anomaly detection to figure out if something's gone wrong with part of the cell tower network. Right? So one day, one of the cell towers starts throwing off network patterns that seem very unusual, then maybe something's wrong with that cell tower. Right? Something's gone wrong. We send out a technician to fix it. It's also used for computer security. If a computer, say if a computer at Stanford starts sending out very strange, network traffic that's very unusual relative to everything that's done before, relative to what is this very anomalous network traffic, then maybe IT staff should have a look to see if that particular computer has been hacked. So these are some of the applications of anomaly detection. And a good way to do this is, given an unlabeled data set, model P of X, and then if you have very low probability examples, you flag that as a possible anomaly for further study. Now, given this data set, how do you model this? Well, one interesting thing about this green dot is that neither the vibration nor the heat signature is actually out of range, right? Like there are a lot of aircraft engines with vibrations in that range. There are a lot of aircraft engines with heat in that range. So neither feature by itself is actually that unusual. It's actually the combination of the two that is unusual. And so that's what I want to do is come up with an algorithm to model this. And in fact, we'll come up with an algorithm that can model, maybe a data density looks like this, right? More of an L shape like that. But how do you model P of X with the data coming from an L shape? And it turns out that there is no textbook distribution, right? There isn't. If you look at the simple exponential family model types of distributions, there is no distribution for modeling very complex distributions like this. So what I'm going to talk about is the mixture of Gaussians model, which would look at data like this and say, it looks like this data actually comes from two Gaussian. There's one Gaussian, maybe there's one type of aircraft engine that is drawn from a Gaussian, like the one below, and a separate type of aircraft engine that's drawn from a Gaussian, like that above. And this is why there's a lot of probability mass in this L-shaped region, but very low probability outside that L-shaped region. Right? And these ellipses I'm drawing are the contours of these two Gaussians. And so what I'd like to do next is develop the mixture of Gaussians model, which is useful for anomaly detection, and then this will lead us to our second unsupervised. So in order to make the mixture of Gaussians model a bit easier to develop, let me just use a one-dimensional example where X is in R. So let's see. So let's say that we get a data set that looks like this. So it's just one row number, so just a number line and plots with a few dots. So it looks like this data maybe comes from two Gaussians, right? It looks like, there's some data from this Gaussian, and there's some data from that Gaussian on the right. And if only we knew, right, which example had come from which Gaussian, if we knew that these examples
that's
had come from
standard
Gaussian 1, which wanted to know with process, and if
oh,
only
so
we
we have
knew,
the data set we want to sorry so we have a a data set mix, and we think they are coming from two Gaussians. We want to find the mean of the Gaussians. They are in a one-dimensional space. What we need to find is first, yeah, that's an interesting question. I like it.
And then this will lead us to our second supervised.
Mathematics is beautiful.
In order to make the mixture Gaussian's model a bit easier to develop, let me just use a one-dimensional example where x is R. So let's see. So let's say that we get a data set that looks like this. So it's just one row number, so just a number line and plots with a few dots. So it looks like this data maybe comes from two Gaussians, right? It looks like, you know, there's some data from this Gaussian and there's some data from that Gaussian on the right. And if only we knew, right, which example had come from
do we know their variance or not?
If we knew that these examples had come
that's not difficult once
Gaussian
you find
1,
the mu.
which wanted to know with process, and if only we knew, but actually this is fine, I'll leave it. If only we knew that these examples
We can use Bayesian to find.
had come from Gaussian 2, which I'm going to draw with O's,
Such
then
a
we just fit
good
Gaussian 1 to the
example.
process, fit Gaussian to the O's, and then we'd be pretty much done. And sorry, and so these are the two Gaussians, and so the overall density would be something like this, right? That's the probability. A lot of probability mass on the left, a lot of probability mass on the right, low, less probability mass on the sort of in the middle. So the overall density, just draw it again. Low, high, something like that. Right? But the reason, and if you actually had these labels, if you knew that these examples came from Gaussian 1, those examples come from Gaussian 2, then you can actually use an algorithm very similar to GDA, Gaussian discriminant analysis, to fit this model. The problem with this density estimation problem is you just see this data, and maybe the data came from two different Gaussians, but you don't know which example actually came from which Gaussian. Okay? So the EM algorithm, or the expectation maximization algorithm,
Okay, let's keep it here. Right? Yeah, that was a good example. I love to see what happens next. By the way, sunlight is coming from your side. I'm going blind. Ah! That's it. Finish! Sorry, AC is on! I have to talk louder. Probably you are hearing Andrew very loud, but I couldn't hear him well. I mean, I could keep up though.